Now that we're into the part of the semester where there's going to be some calculations, I wanted to go through and give you a demo on some calculations that you might have to expect for some of the material that we've covered in the last couple weeks. We're going to start with the rest of the sheet metal working calculations, which is the bending calculations. So we'll get that done tonight and give you some experience like what you might see on an exam. So in front of us here is a question from one of my exams. This is a basic bend force calculation and material bend allowance calculation. So I've given you here some basics for 1/8 inch soft steel. Find the flat length of this part. And then for the same thickness material, now with a material spec 1020 hot rolled and a material width, which is the width of this part, find the force needed to make each bend on a 3/4 inch V die. And this is actually a pretty simple question. The challenge for you may just come in being familiar with using Machinery's Handbook, which is how we're going to find all the information we need here. So we'll start with the first question, which is finding the flat length of the blank. Now really the obvious part here is all the straight lengths are already called out for us. So what we need to find is what is the bend allowance here for these 4 bends. And it says here radius 0.188 4 places. So they're all the same. So we really only have one calculation to do. But what we need to find is the bend radius allowance section, and that's in the manufacturing section of my 29th edition. So we'll come over here to sheet metal working in presses, down to the section on bend radiuses here, bend allowances, page 1347. So if we flip over to that section, it shouldn't take a lot of reading to find what we're looking for, but you're going to want to familiarize yourself with anything that I do a demo on, because obviously that's fair game for what's going to be on the exam. So here under bending, we have inside bend radius calculations, but as we read down, we get to allowances for bending sheet metal. And I have explicitly put here in the question that this is 1/8 inch soft steel. So when we read through our 3 options here for the formulas, we have 90-degree bends in soft brass and soft copper, 90-degree bends in hard, half-hard copper and brass, soft steel and aluminum. So this is the formula that we want. So we can get a piece of scratch paper here and jot that formula down. So we have length equals 0.64 times T in a bracket plus 1.57 times R in another bracket. The 2 variables that we're focused on in this formula, which gives us the length of the bend, is the thickness of the material and the bend radius. So when we look at our drawing, in the question we have 1/8 inch soft steel, so the thickness is 0.125. And then when we look at our radius here in 4 places, we see 0.188. So we plug those in, 0.64 times 0.125 plus 1.57 times 0.188. We can get out our calculator here. We get 0.08 plus 0.57 times 0.188. 0.295, and that gives us a bend radius allowance of about 0.375. So that means we need to make this bend, for each bend, we need about 3/8 of an inch to allow to make the flat blank. Then the rest is pretty easy. we can add up all of our flat lengths here. So we have 1.438, 0.875, 1.875, 1.875, and then 1.312, and then we need 4 of these because there's 4 bends, and 4 times 3/8, you should be able to do that math pretty easily. It's going to be 1.5 inches. We can add all these up. Is 8 7/8. That is the length of our blank that we need to make this part. So that's the answer to that first question right here. 8.875. Okay. Now to do the next question, now we have for 1/8 inch 1020 hot rolled, 24 inches wide, find the force needed to make each bend on a 3/4 inch V die. So we're back to the beginning of this chapter, and now we're looking for press force in bending, and that's in the same section. Actually, I didn't really need to flip back, but it's right there after the section we were just in. So here's the section we were just working on, and if we were to continue reading, we would get to some predetermined tables for what we just calculated, but then shortly after that we would get to other bending allowances, and then eventually we would get to bending force. So we have a formula here for bending force, where force is equal to L, which is the length of the workpiece, times T, which is the thickness of the workpiece squared, times the ultimate tensile strength of the steel over the width of the V die opening. If you can't read that, it's because it's up on the next page right here. So all of those variables are called out. Some of them are pretty easy, because here in the question I've mentioned that this is a 24-inch wide piece. That's the length here. So that's 24 inches. The thickness, again, is 1/8 inch. So that's an 1/8 inch squared. And then the ultimate tensile strength we'll need to look up. But the width of the V die, that's also in here. That's 3/4 inch. So what do we need? We need the ultimate tensile strength of 1020 hot rolled steel. So if we go earlier on in the book to properties of materials, and we get over here to standard steels, then we'll find that there's all the classifications and compositions, but here at the end of the standard steel section we'll find mechanical properties of steels, page 422. So if I flip to that, I'll see some minimum mechanical properties of cold drawn steel, but I mentioned here that this is hot rolled steel. So we want to go to these tables right here. This is mechanical properties for select carbon hot rolled, normalized and annealed. So I mentioned that we have in the question here 1020 hot rolled steel. So if I go here to 1020, as rolled is what we want. That's that one right there. That has a tensile strength of 65,000 psi. So that gives us our ultimate tensile strength of 65 ksi. And we just plug in all of our information. 24 times 1/8 squared times 65,000 in brackets. Of course, everybody remembers their order of operations, divided by 3/4. So we'll clear this. 0.125 squared times 65,000 times 24 divided by 0.75, and we get 32,500 pounds. So that's the amount of press force it would take, a little over 16 tons, to press each one of these in a 2-foot wide piece. So here, 32,500 pounds. When you answer these, I will try to give you the opportunity to show any work that you have. I'm going to review all of your answers. So if you use any particular tables or formulas, I'll try to give you a chance to show those in your exam. These exams I will grade by hand so that we have a little bit more success than we did with the midterm.